Good day. In this video we will talk about gravitational force and weight. So, on top of discovering calculus and discovering his three law of motion, plus work he did on optics, he also discovered the gravitational force, which looks like this. The force of gravity is given by a universal constant, capital G, times one mass times another mass divided by the squared of the distance between the two masses. So let's take one of the masses, let's take the other mass here, and this is the distance in between them. So not square, just the distance. Okay. The value of G that Newton found is 6.67 times 10 to the minus 11. And the units will be newtons meter square over kilogram squared. Now, according to Newton, this force connects every mass in the universe with any other mass in the universe, because the only way the force goes to zero is R is infinity. So this is a long range force. And this connects, this could be the Earth and the Sun, Jupiter and its moons, could be a wall and the paper clip next to the wall. It doesn't matter. Let's consider a special case right now. We're going to put one of the masses is the Earth and the other mass is you. So this is the big mass, this is the small mass. Let's say your mass is 50 kilograms. The mass of the Earth is 5.972 times 10 to the 24 kilograms. And the distance between the center of Earth and you, well, is the radius, which we found the other day. We used it the other day for a problem, and it's 6.37 thousand kilometers. Okay, so let's use this equation and find the gravitational force, which is also your weight, the weight of this person, and it's going to be G. So we're going to plug in all the numbers. 6.67 times 10 to the minus 11. Notice how small the constant is, to the negative 11. Times one of the masses, the mass of the Earth, 5.972 to the 24 kilograms. I want to leave the mass of the person just like m for the moment, and then I'm going to divide this over the radius, 6.37 times 10 to the 3 kilometers, so times 10 to the 6 meters. Let me do this again, times 10 to the 6 meters, and this squared. And what you're going to get is that the force of gravity, or the weight, is this number times the mass. And if you multiply all this, you're going to get 9.81 meters per square second, which is exactly what Galileo found experimentally. And you did too in the lab, times the mass. So this is going to be gm, the weight, or as we usually say, mg. So the weight of a 50 kilogram person will be 50 kilogram times 9.81 meters per square second, or 490.5 newtons. Notice then that the 9.81 is directly linked, well, to the universal constant, but also to the mass of the Earth and the radius of the Earth. If you go to a different planet, that planet will have a different mass and a different radius, so the gravity in that planet will be different. We also differentiate between mass and weight. Weight is the force by which your planet pulls you towards its center. Mass is just the amount of matter you have. No matter where you are in the universe, you will have the same mass, but your weight will change depending on in which planet you are. Even on Earth, if you are on top of a mountain, let's say a big mountain like the Everest, which is 10 kilometers, right? If you are here at the top, well, it's not 6.37 times 10 to the 6 anymore. You are a little higher, and that little bit is going to change gravity also a little bit. So that it might be that at the top of a mountain, gravity is just 9.77 meters per square second and not 9.81. So that's the difference between mass and weight. And this is where this equation is where the 9.81 comes from. Also notice one thing. In this equation, when we speak of mass, this mass is not the same mass that we found before in MA, right? This was inertial mass, and this here is called gravitational mass, which is linked to the force you feel gravitational. Now, experiments show that gravitational mass and inertial mass have the same values, but their meaning is different depending on the equation in which you are using the quantity. I want you to think about this question for a moment. You go into the elevator and you are on top of a scale. This is the scale, right? When the elevator is not moving, that person in the previous page will see 90.5 newtons as its weight. But when the elevator starts moving, the bathroom scale will show different values for the weight. So the question is, are you heavier? Let's say the elevator is going up. Are you heavier, or what's going on? And so think about it. Pause the video, think about it for a few minutes. And once you come back, now we can discuss that what's going on is that you are not heavier. The force acting down is still only gravity. It's still the same planet. So what's going on? Why do you feel an extra force, an extra weight? Well, it's because this is a non-inertial frame, right? The elevator is accelerating, so you feel weird stuff when you're accelerating, when you're moving in a non-inertial frame. What's going on is that in order for you to go up with the elevator, the scale is pushing on you. So what the scale reads is the force it uses against you. When you're not moving, all the scale needs to do is counteract gravity. But if the elevator goes up, then the elevator pushes on the scale and the scale pushes on you to make sure you move up. And that extra force is read on the display. And that's why you appear to be heavier.